Hello, and welcome back. Today, I want to leave the realm of lumped element filters, where filters are built from components that have all of their properties in one single place, and move to distributed element filters, where the components are spread out over a certain area. Specifically, today, I want to look at a set of cavity filters, which may be of use to the hobbyist or ham operator. These include, but are not limited to, things like helical, coaxial, comb line, and interdigital filters. Now, cavity filters have the special property that they can be built with quite high Q factors and also high power handling capabilities, and are commonly used as either band pass or band stop filters. Now, these are some examples of cavity filters that I've previously built and tested. Now, build quality isn't that great, but they do work. We'll get to measuring these next time. But before that, it's important to understand how something like this is even supposed to work. I mean, on the surface, these look just like some wires and boxes. Now, in general, any enclosure made from conductive materials can exhibit electrical resonance at various frequencies, dictated by its constructive dimensions and materials. Various resonance modes can occur, making the problem of analyzing a cavity quite a complex one. The main principle on which a cavity becomes a filter is that when an electromagnetic wave propagates through the cavity, the wave will interact with the cavity's resonant modes, resulting in selective attenuation or transmission of certain frequencies. Now, for today's discussion, I will consider cavities that have some sort of inner conductor, since this is one of the more common constructions used at relatively low frequencies, so ranging from about 50 MHz up to a few GHz. With this sort of structure, we can get a more clear understanding of how the electromagnetic wave exists inside of a cavity. So, at any given moment, you can get an electrical potential developing between the extreme regions and a current passing through, both on the outer and inner conductor. This ends up creating a circular magnetic field and a perpendicular electrical field. So, based on the exact dimensions, this distributed structure will have a resonance frequency where it behaves like a quarter wavelength transmission line, which is shorted at one end and open at the other, and the lumped element equivalent of this being the basic LC oscillator circuit. Understanding how a cavity resonator works is made far easier if we first look at how the lumped element version, the LC resonance circuit, can be built and how that works, since the same basic methods and principles are applied both for putting energy into and then taking it out of the resonant cavity filter, as are for the LC resonance circuit. So, starting from the single LC resonator, we have three main ways of interacting with it when a single port is used. We can have a direct connection, also called a direct tap. We can have a capacitive coupling, where the signal is injected using the equivalent of a capacitor. And finally, we can have a secondary coil, which interacts with the magnetic field. This is also called loop coupling. Now, for the practical cavity filter, there is also a fourth version called port coupling, where the full electromagnetic wave passes through, but I couldn't really find a good equivalent model for that, so we'll just skip it for now. But anyway, if we run the simulation as is, we can check the impedance behavior of these structures. So to highlight that, I created a simulation in which I'm using a current source of AC value 1, so that we can measure the impedance by observing the voltage in the interconnecting node. So if we just plot out all three of these, the first thing that we can observe is that we are getting two very distinct resonances in all cases. At one point, we are seeing a very high impedance value, and at another, we are seeing a very low impedance value. Now, if we just focus on the loop and the tap coupled ones, we are getting more or less the same behavior. The high impedance is before the low impedance, but for the capacitively coupled resonator, the two frequencies are interchanged. So the minimal impedance is first and the maximum impedance is second. Now, because we are getting both types of impedances, both very high and very low values, we can use the cavity resonator as either a band pass or a band stop filter, depending on how it's connected into this circuit. So when this sort of resonator is used as a single port device, we can see what it does when we connect it into a basic circuit. So one in which we have a basic signal source and a basic load. Now, just as a side note, the values that I used in the filter are quite arbitrary, and while the signal source and load are generic 50 ohm devices, but in real life the exact impedances are supposed to be matched. This experiment that I'm doing is just to show the general shape of the behavior. But anyway, if we now run the simulation, and we look at the various responses, and again we just don't plot the phase, we can see that the expected response will be that at a specific frequency, the cavity will create a very strong dip in the signal, so it will greatly attenuate it. And if we just zoom into the upper end, at some other frequency, there will be a maximum. So here, the filter will not be attenuating. So with all three of these circuits, we are getting both the pass and the stop band behavior to a larger or smaller extent. Now, each of these coupling methods has a specific practical implementation which will impact the exact impedance as seen from the outside. Starting from the tap coupling, this is implemented by having a tap running from the external port connected directly into the central resonator. The exact coupling amount and impedance ratio is determined by the height of the tap connection from the ground connection of the resonator. With loop coupling, this is usually implemented in the form of a single turn loop on the bottom side of the resonator. Here, the magnetic field is strongest, so one side of the loop is connected to the outside and the other is connected to ground. Here, the exact coupling amount is dictated by the loop area as well as the angle of the loop in reference to the magnetic fields in the resonator. So when the loop is perpendicular to the resonator, you have maximum coupling, and as the angle changes, decoupling will decrease. Finally, with capacitive coupling, this is usually done at the open end of the resonator, so here the electrical field is strongest, and with this type of implementation, the exact coupling will be determined by the distance of this coupling electrode to the resonator, as well as the surface area. So larger surface area and smaller distance will result in a stronger amount of coupling. Now, although you can build single port cavities, most often you will find these as two-port configurations. The second port is not mandatory, of course, but it does allow the creation of more steep responses. So next, let's see how the two-port circuit can be modeled and used. So I prepared a set of basic examples just to highlight the single resonator two-port design and connected it to the same types of signal source and load as we had before, just so we can see a good comparison. So I have both the two-port designs as well as the single-port designs. So if we simulate this, we can start by looking at tap coupling, and well, here, it's basically the exact same circuit, as long as both taps for the two-port design are going into the same point on the resonator. So with this use case, there's absolutely no difference between the two-port and the single-port design. If we now move to loop coupling, I added the same type of inductance for the two-port design, and I also kept the same coupling factor as we had before. And well, if we now compare the results for the single port and the two-port design, we are getting a more pronounced bandpass effect and a stronger out-of-band attenuation. So when passband filtration is needed, the two-port loop-coupled resonator is working better. Finally, if we move to capacitive coupling and plot out the two results, well, we started with a very clear notch effect with the single-port design, and in the two-port design, we transition to a very clear bandpass effect. Now, in general, single-port cavities will be used as notch filters, and two-port designs are more commonly used as bandpass filters. So this is quite common for all of the coupling types. Finally, it is worth mentioning that in certain cases, you will be adding extra parallel components in between the two ports to get some new effects. So for example, you can add capacitors in parallel to the loop-coupled designs or to the capacitively coupled designs. So if we quickly compare the basic loop-coupled two-port design, and we also add this capacitor in parallel, we can get a far more pronounced bandpass effect, with a very clear wide dip at high frequencies. For the two-port capacitively coupled circuit, if we add in the parallel capacitor, well, we get an extra very sharp dip at frequencies lower than the passband. Now, other than these two, other combinations of values and reactive elements can be tried, of course. So you will also find inductors or other things added in parallel with the resonators. Now, having a single resonator is nice and all, but what if you need a more intense effect? Either stronger pass or stop band filtration? Well, you get more resonators. And here we get the next topic to discuss. How do you interconnect multiple resonators? Well, there are two main ways to do that. So, when discussing more than one resonator, we either put a transmission line in between, or we build the resonators one next to the other and transfer energy through port coupling. Let's take these two one at a time. So, starting with the cable use case, first of all, any transmission line will end up creating a certain impedance transformation effect. Based on the transmission line length and signal frequency, the impedance from one side will be seen as something else from the other side. And this is not something that we always want. However, there are two very specific cases of this impedance transformation to keep in mind. A quarter wavelength cable will change the impedance from one side to the other based on the cable to environment mismatch. There is quite a nice formula for this. And the second important use case is the half wavelength cable, where the cable's impedance does not matter. One side will see exactly what is on the other side, regardless of what impedance the cable has. But you can of course use some other length of cable and rely either on some impedance matching property, like the quarter or half wavelength, or just induce a specific phase shift that you might need in between your resonators. Now, the other major approach is to build the resonators one next to the other. Basically, have the cavities touching. No more cables are involved here. And with this approach, you can either have a full-size gap running the entire length of the cavity, or you can have some sort of smaller gap, either fixed or adjustable. So these two cases are port coupling in a nutshell. Now, you no longer have the option of adding any sort of delays, like you had with cables, but with this approach, you should have minimal losses. And based on the opening dimensions, and well, the distance in between the resonators, you can adjust the exact coupling in between them. So this is how you will adjust the bandwidth of your filter. Last thing to discuss today are some of the common constructive types. Cavity resonators and filters come in all shapes and sizes, but there are a few that do stick out. So one of the simplest shapes is the coaxial resonator. It's a basic cylinder with a center rod and one or two coupling ports. The coupling is most commonly of loop type in this case. Now, these are used at relatively low frequencies as single units or as interconnected sets. The next significant variation is the comb line filter. This is a relatively long filter cavity with multiple resonators all connected on the same side of the enclosure. So all of them are connected to ground on the bottom in this case. Now, although multiple implementations exist, this is most commonly built with tap coupling at either side of the cavity. Now, a variation of the comb line is the interdigital filter. The difference between these two is that at every two rods, the connection to ground changes. So once it's on the bottom, the next is on the top. This means that there will be a difference in the electric and magnetic field coupling in between the resonators. So this will change the size and the bandwidth of the two filters. Finally, in a similar fashion to how a straight antenna can be replaced by a shorter helical antenna, you can have helical resonators. You can build all of the three previous structures with helical resonators, greatly reducing their size. So this sort of construction is especially important at relatively low frequencies where size is of major concern. Now, in general, helical resonators are tap coupled, and while the main disadvantage compared to the straight center conductor is that this sort of filter will have higher losses in the passband. In the end, cavity filters see a wide range of usage in things like small signal filters in various receivers or scientific equipment, but also in high power filters, in things like repeaters. Even though this sort of filter can be acquired commercially, it's one of those things that the average amateur can also build themselves. So next time, we will look at how well the simulations match real life, and also what sort of performance you can get by testing out some practical filters. But until then, hope you enjoyed this video, and if so, there are more similar videos on my channel that you might want to check out. And if you want to be up to date with my latest releases, also consider subscribing. See you next time. Bye bye.